Welcome to another Great Car Basic training session. So today we're on part 20. So what's part 20? Part 20 is looking at how Great Car Basic produces PIC and AVR ASM, the layout of the file, and we're going to be looking at a source file and using a thing called MPLAB, but you could be using any other tool. Okay, so how have we got to where we are? We've covered 19 so far, and then tomorrow we'll be doing programmers, and then I will call it a wrap for this set of programs. So we're going to be looking at assembly and alternatives. So I've got a PIC. As you'll find out today, it could have been any PIC. I happen to pick a 16F 18313, and by now you'd have thought I got that sorted, and it's connected to a PIC-Kit2 programmer. I was just checking then. Okay, it's got 8 pins and it's got some ports. Now today, this is the board itself. Let's have a look at that in reality. There we go, there is the board itself. It looks very similar. I've taken 2 of the bottom LEDs out, and that's because I needed, so I can lean across, that was all. Let's look back at the PowerPoint, and we're going to be looking at programming just one LED, the top LED, the green one on the top right. So why would you want to do this ASM thing? Okay, so one is for education. You might actually be doing an education program where you need to look at how assembler works. You might be optimizing code for a specific microcontroller. I'm a bit optimistic about that one in the context of Great Cal Basic. But you might be looking for enhanced reporting. Okay, so you might be there looking at how assembler works to understand the process. Secondly, you might be looking at to optimize some program that is very specific. Okay, or Great Cal Basic doesn't cover that capability. Like you've got your own macro, you want to suck it in. Okay, and then as I said, enhanced reporting. So what we're going to do is look at the assembler that, or ASM, that is produced by Great Cal Basic. We're going to create a simple program and test that, and then that's just to prove that you can use inline assembler. And then I'm going to use some alternative software to create enhanced reporting and produce a hex file. So yesterday we saw this diagram, and really saying that the compiler itself is the core. It can generate object machine files for about 1,000 microcontrollers, and it supports PICs and AVRs. And what we saw yesterday is that it's got a set of components. We take the high-level source code, and let me just put a pen on. We take your high-level source code and we import the libraries. So we take your source code and libraries, we pre-process out, we put it into a code translator, then we assemble it. We produce at that point linker files, text files, and HTML reports, and we output an ASM file. And then if that's how you got it set up, we'll go straight into our internal linker and we'll produce a hex file for you. Well, what we're going to be doing is this today. I also showed this in session 19, where we're actually going to stop the Great Cal Basic process here at the edge of that right-hand blue box, and we're going to use today. I'm just going to be using MPASM. You could use GPASM. I have installed it, but I haven't got time to show you. And we're going to take an assembly language file, and we're going to then produce a hex file. Okay. So let's get cracking on some coding. Let's look at the code I produced in preparation. So I've produced a very simple file. Let's just go through it. I've specified my chip, and all I'm going to do is turn the LED on. Okay, and then we're going to use that as our example for today. I've got option explicit, which means I must define my variables. I define a variable. I set that variable to 1. I could set it to 1 means on, and let me just turn that on for you. On. Then I set the port out, and then I'm going to set an LED to that state of the LED. So I'm going to set the port, okay, to that LED state. Let me just program that up. I need to save it. It's not spelled correctly. There we go. I've just saved the file and we're programming it. We are indeed. Great. And we should see the LED come on. And if I zoom in on that, we can see that the LED is actually is on. That LED, that red LED is on. So what has that done? How did it do that? Well, this code, and not these comments, we'll come back to the comments here in a moment, has produced an assembler file. And I can look at the assembler file by going into pressing Shift F7 or into IDE Tools, GCB Tools, and Open ASM, which is what, the fifth option down. You can't see that. I'll show you on my desktop. IDE Tools, GCB Tools, Open ASM. And then I'm in the ASM file. I'm looking at the ASM itself, okay? Let me take you through the structure and then we'll do some coding, okay? All right. Well, this complies with the microchip standard. We have a header file which talks about the originator. This is Mr. This is the gentleman that wrote the code. It's not his real name, so I'll keep quiet. It's got the version. Anything in green is commentary, so just ignore that. What we're looking here at, we're looking here for the specification of the chip and the radix, which is we're working in decimal, and then we set up the configuration for the chip. Great Cow Basic in assembler does that for you. Then we always set up your variables for you. Swig of coffee. Great Cow Basic manages the memory for you, and then we set up where the code sits in memory. We set it AUX0. Now we do this automatically, so you don't have to worry about it. But basically, it sets it up in the lower part of the memory, and then it jumps to. It says go to program start, which it does at a memory address, and then it calls an initialization routine. And this is all in assembler. And then it goes into our program. So let's have a look at this thing called initsys. On the left hand side of my screen here, I can double click it, and this is the assembler for setting up this particular chip. And it always calls the initsys. And the knowledge that we have to pre-set up 1,000 chips is embedded in our code in our own libraries. And if I can show you, this sets up one register, this sets up another series of registers, and then we set up the ports for you automatically. This is raw assembler. But if we cursor up, we can see the main body of our program where we're setting this LED. We're setting the state of the LED, and it says two pieces of assembler. It says set the W register to 1. I am not going to teach you assembler today. I'm going to show you how to do it. So if you know how to use assembler, you can learn from this. And then it moves that register into a variable, a memory state of memory position, which was 32 from memory. Sets the port as an output, and then sets the port A1 to the state of LED state. So why don't we just take a copy of this code here, right? And I've taken a copy of the code and come back into our original training program and just comment out this stuff. Now, I've left the dim in because Great Cow Basic manages the memory for you. So you just need to declare your variables. I'm going to take this assembler, push it in, and have a look through it. So here we go. Here's the comment. If you want to learn how to set a variable to a value, this is how you do it. So if you wanted to set it to 0, you put 0 or any other value in here, and then you can look up what this command actually does in assembler. Then it moves it to the memory position, sets the port as an output, and then it sets it selects the port itself, clears the bit, BCF, clears the bit, or sets the bit. Now, if I try to assemble that, because this is now inline assembler, I will get some errors. I get some errors, and they're all the same errors. Bank cell, bank cell, bank cell. That's because Great Cow Basic looks after the bank cell for you. Now you can You can force it in, or you can just comment it out. It's up to you. Bank cell is the selection of the right bank of memory for that particular operation, and we do that automatically. So if I just comment out the bank cells, if I could do that, or let me just delete them, because it will be clean then. If I delete them, the code will be clean. We've now got raw assembler sitting inside of Great Cow Basic. I'm going to change the LED to LED 2, because I'm hard coding this stuff now, okay? And if I then, I got an error, which I did not expect. Oh, I know why. Because the end if statement is a label, and I need to turn it into a label. There we go. Turn it into a label and compile that up. Well, I've just turned the camera on. This was the red LED that was on previously. We've now turned on the yellow LED. So this is inline assembler. We look back here in our source. I can see that it's generated our code as raw assembler. So it's taken the raw assembler from our program and put it into the assembler. Now, what's interesting about not doing that is if I go back to my original program, which was setting up the red LED, that's called portable code. It will work across any of these chips. I've selected these at random, okay? Because if we look at our assembler again, remember the header we looked at here? This is very specific to this particular chip, an 18313. If I change that to a 18F and I generate the assembler, you will see it's changed the command, it's changed the header, and the rest of this has changed as well. We write portable assembler. If you use Great Cow Basic high level language, it is portable. When I was doing the assembler previously, this code that I had in here, it is, so I'll restore it. This code is not portable. You have no guarantee it's going to work. Now, you might say it's not important to yourself. That's fine. I get that. So let me just restore that. Let me change that chip there to a, let me just comment that out. I'm not sure if this is going to work because I don't think there's a port A on an AVR chip. So I might have to just change the port here to make this work for us. No, there's no port A, so that's valid. That is valid. There is no port A. Okay, there's port B. And I'm going to generate the hexadecimal file for that, the ASM, sorry. Open up, look at the ASM. It's now changed this to AVR assembler. So we generate raw ASM. Okay. Let's look at another reason. So if you wanted to learn assembler, you would just use our tool and you can just wade through to your heart's content. You can wade through to your heart's content learning assembler. There we go. I will put our code back. Now, what's interesting is it's generated this assembler file. We generate reports. We saw those yesterday, but I'm now going to show you how to generate those reports inside of a different assembler, a linker tool. And that linker tool happens to be part of MPLAB X. So if you go to your MPLAB installation, you select your version, you will find a folder called MPLAB X, MPASM X. Click on that, like this. Let me show you like this. So I've selected my MPLAB installation. My version is 5.30, yours will be different. MPLAB X, MPASM X, and in here there's a Windows application called MPASM X. Open that up. All I need you to do to show you this is take this, take the source code here. So if you do full path to clipboard, which is the fifth option here, full path to clipboard, we're just going to put that inside of this tool we were looking at called MPASM. Put the file name in here. I haven't got the file name in here yet. There we go. You might have to put quotes around it. And then select a number of options just to set it up. Radix is default. You could select decimal because we work in decimal, but it will read it from the source file. Errors only is good. Default. I want you to check all these generated files 1 through to 4 because we're going to look at them, some of them. Uncheck case sensitive. Uncheck extended mode and assemble. And we get a green light on the assemble, which is great because it means it's assembled. So the third reason I'm showing you here is you might want to use this reporting that's generated. So I'm going to open up those reports by looking in the folder, and I can see there's an error file, a list file, and an XRF file. I'm going to open those up, and we can see we've got the standard MP ASM X files. We've got no errors, it's empty. If I had an error in my source code here, let me just think how I can put an error in here. Let's change that to port B. Oh no, we won't do that. It's just too complicated. This is the list file. This is absolutely generated by MPASM 5.86 to prove that we're generating assembler. And you can see the commentary in here. You can work your way through how the code is generated. And then you've got a cross-reference file which will tell you exactly what's been used. So in here you will see the inc file, and that's the include files provided by Microchip. And here is our source, and it says something it's line 102 in this file has set up the AD COM. So what you can do in here, you can work out exactly what our code is touching. So we've actually set up the format of the AD for you on line 102. We've set the answer, and you can work through this. So if you wanted a full detailed report of what we're actually doing in the assembler, you can use MP-ASM-X and understand that, okay? So what I wanted to do today is show you, let me just go back to what we're trying to do, is review some structure. So we've looked at a high level structure. We have the header, we have the BAS start, init sys, and then we're into your own code. We've taken a simple piece of assembler, which was LED code. We can compile that up, so we can compile inline assembler. And finally, I've used an alternative linker to take our ASM file and put that ASM file into a hexadecimal file. So with no more to do, I think we'll call that a wrap, and thank you.